Okay, we have so far studied cases where angular momentum is conserved. We looked at the cases where a child walks out, whatever, and then we look at the collision process, right? In any of these cases, we have conservation of angular momentum because the net external torque happens to be equal to 0. But the most general case is when the net torque from the external source may not be equal to 0. So then what happens is that you are going to change the angular momentum of the system. How much does it change if the torque provided by external source is not 0? Well, that's something we're going to study now. Okay, and the result is so-called Angular Momentum-Angular Impulse Theorem. Remember the Momentum-Impulse Theorem that we learned in Chapter 9 for linear collision, for collision conservation, for collision which changes linear momentum? Okay, what we had was this. What we had was external force equals to dp over dt, right? dp over dt. And I say, I want to know how much the momentum has changed. So I want to integrate over dp. So to do so, before I can do that, let me move dt to that side and let me integrate. Then I have f external dt equals dp and integrate both sides. This is just delta p. And what do we have here? The time integral of f over time, that is called impulse, right? Linear impulse is simply called impulse. We call it J. So the external impulse delivered by a force equals the change in linear momentum in the meantime. So that is the most general case when you do not necessarily have conservation of linear momentum. How much is the change in linear momentum? That equals the impulse delivered by an external force. And if, of course, should the external force be equal to 0, then this impulse will be 0 and delta p is equal to 0. You go back to the conservation of linear momentum. Okay, what we have here is different. We have an angular case, but it's analogous. Okay, we have external torque equals the rate at which angular momentum L changes. Okay, if external torque is not equal to 0, then the angular momentum will change, but how much is the change? We do something very similar to this. Okay, let me figure out what dl is. Let's integrate to find delta L, the change in angular momentum. So dl equals to, move that dt over, just what we did for the linear case, tau external dt. Okay, what is the change? That's the infinitesimal change in L. What's the total change? I must integrate over time interval. Okay, so from t initial to t final. Meanwhile, L went from L initial to L final, right? Okay, this side is simply delta L. So it's L final minus L initial. The other side is this integral over time. Okay, is this integral over time, torque over time, T initial over T final, external torque dt. This is called angular momentum-angular impulse theorem. It says that the time integral of external torque, which by the way is called angular impulse, just like here this is linear impulse or simply called impulse. This is the angular impulse, equals to the change in angular momentum delta L. Okay, so linear impulse changes linear momentum, angular impulse changes angular momentum. That is the angular momentum-angular impulse theorem. So even though we may not have conservation of angular momentum, at least we can figure out how much it has changed if I know the angular impulse. Now this integral, by the way, I can approximate it. Suppose I know roughly the time interval is delta t, and roughly I know that the external torque has a certain value. So I can figure out the integral roughly by using this rough value of torque times the time interval delta t. And suppose I know the average value of the external torque. Okay, then I can work this out into an exact formula for this integral. It is just torque average value times delta t. That is the definition of average value. You just take this integral divided by delta t. Okay, so if I know the rough value of average torque and time interval of delta t, I can figure out the change in angular momentum. Let us see how we can apply this formula to study a case where angular momentum does change. And that is the physics of playing the pool. You know, the game of pool. You use a billiard ball to strike use a cue to strike a billiard ball. You know, the game of pool is interesting because you're mixing the linear motion of the ball, of the billiard ball, which moves from place to place, with rotation. Okay, with rotation. So you have both translation and rotational motion. So the physics is rather interesting and makes the game more interesting. You have more ways to control the movement of the ball. One thing you do is, if you play pool, you know what I mean. If you strike the ball with a cue, the resultant motion of the ball depends not only on how hard you strike it, but also where you strike the ball. Suppose you give it a horizontal strike, okay, a distance x above the line which contains the center of mass. Okay, so you strike it above it. What is x equal to? Well, it turns out the value of x, that's where you strike it, will affect the motion of the ball. You probably have this experience if you play pool, that if you strike with a fairly large x, so x is almost equal to r, okay, so you strike it near the top, then what happens is that after you give it a brief strike, the ball will start moving, right? Not only will it start moving, it will go faster and faster and faster before it settles down into a pure rotation state. It goes faster by itself, okay? It goes faster by itself as if somebody's pushing it after the cue is no longer pushing it. Actually, there is an external force, of course, otherwise it's not going to accelerate forward, and that force must be from the only suspect, right, which is, you know, the table. Okay, so the table must give it up forward push. How come it's doing that? Well, we can investigate that. Okay, but as a matter of fact, if you strike it very low, okay, strike it say here, then after the collision, you are going to see the ball moving forward, but it's going to slow down before it settles into pure rolling, and that is called, that means there's a force pushing it backwards. The first case where the ball accelerates on its own is called forward English. That is a term for this type of behavior, forward English. And notice here, the letter E is not capitalized. It's called forward English. Anybody who plays pool knows what I'm talking about. And if you strike it lower so the ball goes backwards, not backwards, the ball goes forward, but it slows down as a result. It's called backward English. Backward English. And it turns out if you strike the ball not too high, not too low, but in one given spot, one right spot, then after you strike it, the ball keeps on rolling. It does not speed up, it does not slow down. What is that x equal to? Well, let us investigate that. Okay, let's look at the physics of this process. You know, from the previous example, we learned that sometimes it's a good idea to mentally separate the process into several stages or several steps. Here, let us look at the motion of the ball. We separate into 3 stages. Stage number 1, the cue gives a horizontal impact to the ball, and that is a very sudden process. Okay, the ball hardly moves as a result right after the collision, because the collision is very brief. Okay, the ball will acquire a linear momentum and an angular momentum, of course, due to the impulse delivered by this force. But it's a very brief moment. Let us investigate what happens as a result of this very brief impact. That's stage 1. Stage 2, the impulse is done. Okay, the cue is no longer touching the ball, so the ball goes forward on its own. It is still touching the table. The table may give it a friction, which may speed it up or slow it down. But eventually, after rolling a little bit, it's going to settle into what's called a pure rolling, as we studied before, so that it is no longer sliding forward or sliding backward. That is the final stage, stage 2. So you get 3 stages again. Striking it, that's stage 1, and then the ball starts to go forward, and there was a little bit of sliding here at the contact point. That's stage 2. And stage 3, you don't have any sliding anymore. It settles into pure rolling, whereupon the speed of the ball does not change anymore, except air friction can slow it down. Okay, let's look at these 3 stages. Stage number 1 is a very brief delta t, during which there is a large but brief force F delivered by this Q horizontally on the ball. I really don't know what this F is, okay? But I do know that force, F, whatever it is, serves 2 purposes. One, it delivers a linear impulse to the center of mass of the ball so that the center of mass acquires a linear momentum and starts to go forward. And secondly, because it's off-center, it's not delivered right on the center of mass. So relative to the center of mass, this angular acceleration is not 0 because, after all, there's a torque F times x. And you take that torque delivered over a certain amount of time, that of course is an angular impulse, and that's going to create an angular momentum for the ball so that it does not, it starts from rest and now starts to roll, okay? It has a new angular momentum. So, again, that's the two things this force achieves. It gives you an angular momentum and the linear momentum at the same time. Let us look at how much linear momentum the force delivers to the ball as a result of this impulse. Let's say on average the force is F bar. I don't know what F bar is, but if I did, then I know that F bar times delta t, which is the time of impact, that would be the linear impulse, right? The linear impulse equals the change in linear momentum. Before the collision, the linear momentum was 0, and after the collision, it has a linear momentum m times v naught. What's v naught? It is the speed of the center of mass of the ball right after the collision. Linear speed of the center of mass right after the collision. Okay, that's what happens as far as the center of mass linear motion is concerned. And then you have rotation. That is the angular impulse, angular momentum theorem. Be careful when you apply torque and angular momentum, that sort of thing. You only can consider 2 types of points, either a fixed stationary point or the center of mass. During the impact, there can be sliding going on. So point A is no longer necessarily the axis of rotation. Okay, you don't have pure rolling necessarily, so therefore, let's be careful here. Let's use the center of mass, point O, to calculate torque and angular momentum. That is always foolproof. Okay, so relative to this point, here is the lever arm of the force. So the force delivers an impulse of F, a torque of F bar times x, okay, times x. That is the torque, F bar times x. And then times the time of action, delta t, is the same as delta t there. And that equals what? The change in angular momentum, okay? Before the collision, the angular momentum was 0. After the collision, suppose it starts to roll forward, of course, it rolls forward with an angular speed of omega naught. Then, of course, measure from the center of mass, the angular momentum is ICM, or IO. O is the point right here, that's the center of mass, times omega O. Okay, I use these 0, 0, 0, O, O to denote these are the quantities right after the collision. VO is the linear speed of point O right after collision, and omega O is the angular speed about the point O right after the collision. You know, I don't know what F bar is. I don't know what delta T is. But I can eliminate both of them simultaneously with one trick. And what's that? You take this equation divided by that equation, right? You see? F bar and delta T are both gone simultaneously. So that certainly is something I want to do. So what's left is just x. You take this divided by that, just x. So what's x equal to? X equals to I O omega O divided by m v O. Suppose it's a uniform sphere of mass m, radius r. I O about the center of mass, 2/5 mr squared. Okay, so that is 2 m r squared omega O divided by 5, 2/5 mr squared divided by m v O. Let's work it out. What's that equal to? 2 m and m cancels, r squared. So omega O r squared over 5 v O. X is determined by where you strike it, and it does not change. Okay, once you strike it where you strike it, and x is fixed. But as a result, you see, you have initiated both rotation and translational motion, right? As a matter of fact, we can solve for VO now. VO equals to 2r squared over 5x times omega O. You know, it's proportional to omega O. That makes sense. If the force delivers a lot of angular impulse, it must also deliver a lot of linear impulse. So you can go faster, you can rotate faster. There is a constant of proportionality here, 2r squared over 5x, depending on where you strike it. Okay, so that is the end of the first stage. You acquire some linear speed and angular speed. Now let's look at the second stage. The second stage starts the moment the cue stops hitting the billiard ball. So it starts to go forward and rotating at the same time. This is the moment when it just starts, the second stage. Okay, it is at this moment, the center mass, point O, is moving forward with speed VO, and yet the whole thing is rotating forward with a speed omega O. Now, let's look at point A. Point A, that is the point of contact. Okay, is the ball moving at point A? In other words, is the contact point of the ball sliding forward or backward against the table? Let's see now. If you look at using point O as a reference, okay, then it's not moving, right? And then from the point O point of view, this point A is going backwards, right? Because of rotation about it, right? How fast is that speed? It's omega O times R, the radius, right? And that's backward speed. So there is a backward speed, omega O times R, due to the rotation, like this. But on the other hand, point O is actually moving forward with a speed VO, right? So relative to point O, it is going backwards. What about relative to the table, to the ground? Actually, it's VO minus omega O times R, right? So VA, the speed of the contact point of the ball relative to the contact point with the ground. There's a forward speed VO due to the center of mass motion, and there's a backward speed omega O times R due to the spin. So the net speed forward is VO minus omega O times R. Now, there are three possibilities, of course. Is it greater than 0, equal to 0, or less than 0? Let's look at these three possibilities. Okay, let's look at these three possibilities. If you have greater than 0, that means overall the speed is still forward at this point. Okay, in other words, the ball slides forward at the contact point. If the ball slides forward at the contact point, then if there is a static friction between the table and the ball, of course the table is not exactly icy, right? I mean, there is traction, there is friction. So the ball wants to slide forward, right? Want to slide forward. So what happens? Well, friction is always against the tendency of motion, therefore automatically you get a backward friction. There will be a backward friction, Fs. And what does that friction do? That friction does two things. First of all, it is backward, which means it's going to slow down linear motion, right? It's going to slow down linear motion. So then VO will go down. Okay? It is no longer, as time passes, no longer as big as it was before. But what happens angularly? Well, about the center of mass, now you have a friction going this way. It's going to cause it's going to cause a clockwise torque, which means omega O is going to go up, right? So here's what this force does. It slows down linear motion, but speeds up the rotation. Remember, you started with VO greater than omega O times R. That's why it's greater than 0. Okay? So what happens is that VO is going to go down, omega is going to go up. So eventually, it's not positive anymore. It becomes smaller and smaller, eventually becomes 0. When VA becomes 0, you have reached third stage, what's called pure rolling. This point is no longer sliding forward or backward. Therefore, you have a pure rolling. The friction automatically stops. You don't need any friction anymore, and the thing simply starts to do pure rolling. Okay, now, on the other hand, if VA is less than 0, which means VO is less than omega O times R, that means you have too little linear motion to begin with and too much angular motion. Okay, too much turning. And that means you're going to have a large backward speed due to rotation and small forward speed due to translational motion. So you're going to slide backwards. Okay, at this point you're sliding backwards, which means friction being against it, as always, is now forward. So Fs is forward. What does this Fs do? Well, first of all, it's going to increase VO. So that's why you go faster. Even after the cue leaves the ball, friction from the table will push it forward. It's going to go faster. That's where forward English comes from. Okay, but on the other hand, this friction causes a counterclockwise rotation about the center, right? So therefore, it's going to decrease omega naught. Okay, so you start with this less than 0, so VO is too small, omega O is too large. But then due to the friction, VO is going to increase, omega O is going to decrease. So eventually, VA will become 0, just like here. VA approaches 0 here again. VA after a while becomes 0 again. So you see, automatically, there is a friction. I shouldn't call it static friction, by the way, I'm sorry. Kinetic friction, because there is sliding going on. Okay, there is a friction from the table. That friction adjusts the relationship between VO and omega O, so that whether you start with too much translational motion, like in this case, or too much rotation in that case, that friction automatically comes in to adjust friction, to adjust translational and rotational motion for you, so that eventually you will reach pure rolling. What happens at the pure rolling? That's stage number 3. The speed here is 0. So VA, which is equal to this V minus the final omega times R, and that equals 0. Okay? There's no tendency for this point to either go forward or backward. Everything is rotating about this point. Friction, I should say if Fk, either Fk or Fs doesn't matter, because this one doesn't move. Simply becomes 0. Keeps on rolling forever like this if you don't have air friction. This is stage number 3. Okay, so when do you have forward English or backward English? It is now clear once you understand these 3 stages. Forward English takes place when the ball goes faster by itself because of a forward push by the kinetic friction. So that is forward English right here. Okay? You don't have enough linear speed, so friction comes in to help you to increase linear speed and decrease rotational speed. And that happens when VA right after collision is less than 0. So here is the condition for forward English. Okay, forward English. VA is less than 0. In other words, VO minus omega O times R is less than 0. That is the condition for forward English. And we know what VO is, and we know what omega O is. In fact, look at this formula here. VO equals this constant times omega O. Okay, so let's plug that in. Okay, I have 2R squared over 5x omega O. That's VO, right? Minus omega O times R. That has to be less than 0 for forward English to take place. You cross out omega O and omega O. You can solve for x. Okay? So what is x equal to? X must be greater than 2 over 5r. That is the condition for forward English, which means when you strike the ball, x has to be higher than 2 over 5 times r. You must strike it pretty close to the to the top of the ball, and that's how you cause a forward English. Okay, if you strike it lower than that, you're going to get backward English. And what if you strike at precisely 2 over 5r? What happens if x equals 2 over 5r? Well, if x equals 2 over 5r, then this formula, that's VA, right? Would be equal to 0, right? Because this term equals that term. And VA is equal to 0. What does that tell you? It tells you right after the collision, right after the cue strikes the ball already achieves pure rolling because point A happens to have 0 speed. You can bypass the middle stage where there is either backward FK or forward FK. Okay? Because pure rolling has already started. You don't need any friction to adjust linear or translational speed for you. They already satisfy the condition for pure rolling. That means if you strike it at precisely 2r over 5 above the center of mass line, then right after the collision, the ball will simply roll forward in pure rolling. It is not going to speed up. It's not going to slow down. Okay, so that is the only spot you can strike it so that the ball will keep on rolling at the same speed afterwards. So once again, the important thing I want you to learn from this particular example is to mentally separate a process into different stages and understand it, each stage separately, using appropriate physical law to address the physics of each stage. In this case, after the collision, you have the speed at sliding speed at the contact point greater, equal, less than 0, and you can figure out VA using the impulse momentum, angular impulse, angular momentum theorem, and that if VA is greater than 0 right after the collision, the point want to slide forward, friction is backward, and you go what's called backward English, it's going to slow down. And if VA is less than 0, that the contact point slides backwards, the force of friction is automatically forward, that is forward English. Okay, in the middle point, of course, when it's equal to 0, you're just perfect, you strike in the right spot. Point A does not slide at all, either forward or backward, and the friction is simply 0. The speed will never change afterwards.